Hi, this is the visual abstract of study on mechanical wear, corrosion and fracture characteristics of aluminum 7075 by modifying nano-sized magnesium element. Adding magnesium to aluminum alloy often increases the strength and hardness of the material. However, too much magnesium can weaken the toughness and ductility. Therefore, while developing aluminum magnesium alloy, it is very important to balance the desired features and trade-offs. The importance of different elements for improving alloy characteristics has been studied in the past, but there are very less investigation on the impact of main alloying elements. So in the present investigation, we have studied the impact of magnesium modification at nanoscale on mechanical wear, corrosion and microstructure of aluminum 7075. In the present investigation, aluminum 7075 was used as a base material. 30 to 50 nanometer sized magnesium particulates was used as a modifying element. The modifying elements were varied from 0% to 2.5% in steps of 0.5% within all the cache samples. The coke furnace was used to melt the base material. When the base material is converted into molten metal, the required weight percentage of magnesium particulates in terms of nano sized were mixed into the molten metal and stirred for 15 minutes. When the modified molten metal was ready, it was poured into the preheated mold box and allowed for solidification. After solidification, the obtained modified cache samples were removed from the mold box and machined the samples according to ASTM standards by using CNC machine. Figure 2 shows the optical microstructure of the base alloy and nano-sized magnesium modified alloy. From the outcome, it can be observed that uniform distribution of particulates taken places. Figure 3 shows the ED spectrum of base alloy and nano-sized magnesium modified alloy. From the outcome, it can be observed that more number of the magnesium element was found by the ED spectrum. Figure 4 shows the micro-hardness of the nanomagnesium modified alloy. The hardness of the nanomagnesium modified alloy was increased up to 0 to 2% due to the brittle phase of the nanomagnesium particulates, whereas in the 2.5% the hardness was reduced due to the interdislocation moment. Figure 7 shows the impact strength of the nanomagnesium modified alloy. Here, due to the high brittleness of the nanomagnesium particulates, the impact strength was reduced. Figure 5 shows the tensile strength of nanomagnesium modified alloy. From the outcome, it is observed that up to 2% of nanomagnesium, the tensile strength was increased due to the high brittle hard particulates. Whereas in the 2.5% of nanomagnesium modified alloy, the tensile strength was reduced due to the agglomeration of high weight percentage of nanomagnesium particulates. Figure 6 shows the fractured surface of the tensile samples. From the outcome, it is observed that more number of cleavages was found in the base material, whereas in the nanomagnesium modified alloy, the fractured surface was seen that more number of dimples was found, and this dimples indicates the fracture was ductile fracture. Figure 8 shows the wear loss of the nanomagnesium modified alloy. Due to the high hardness, the material was very good resisted for the wear and tear. So, by increasing the nanomagnesium particulates, the wear rate was reduced. Figure 9 shows the worn out surface of the base alloy and nanomagnesium modified alloy. In the base alloy, the worn out surfaces can be observed that more number of scratches, but whereas in the nanomagnesium modified alloy, Deep grooves and plastic deformation was found. The figure 10 shows the corrosion rate of nanomagnesium modified alloy. Here, due to the reaction of magnesium particulates, the high corrosion rate was found in the modified alloy. From the same image also, it can be observed that base material have been corroded very less compared to the nanomagnesium modified alloy. Conclusions. Magnesium's reinforcing function in the aluminum alloy was highlighted by the optical microstructure study, which showed uniform distribution of nano-sized magnesium particulates in the alloy. Tensile strength, hardness, wear resistance, and corrosion resistance improved by 9.21%, 15.73%, 18.82%, and 23.80% respectively in the nano-sized magnesium modified aluminum 7075 alloy. The intermetallic phase reduced their effectiveness in hindering the dislocation of motion. Therefore, addition of 2.5% magnesium aggressively affect the strength improvement compared to the alloy containing 2% of magnesium particulates, which was observed using fractured surface SEM analysis. Thank you.